Greg said, my name's Rob DiNardi. I'm president of L&S Machine Company. We're a company located in Latrobe, Pennsylvania. We're a manufacturing company. We're 90 people in Latrobe, and we recently acquired a company in San Jose, California. We're 17 people in San Jose, California. We build a variety of products. Mostly I'm going to tell you about our Latrobe facility, what we do there, and what we do with predictive statistical process control. Here's some of the things we make and why that's important. These are fuel nozzles that go into a nuclear reactor. And the reason we went to, I'm going to give you a little history of why we did this. The reason we went to statistical process control is that obviously when you want to buy nuclear fuel, you want it to be, the dimensions to be proper all the way through. So we do 100% inspection of all these parts. And we couldn't do any statistical process where we would do random samples. It has to be 100%. Now, our machines, let me see. Well, a little bit of background on us. It formed in 1954. I bought the company in 2007. Biggest customer right now is Westinghouse. We do build fuel for 50% of all the reactors in the entire world. 70% of some of the fuel nozzles and 80% of the springs are built by us. So, and we're the only domestic producer. If you have a reactor in the United States, we build the product. Pretty good for a small company in Latrobe, but that's what we do. We have 23 vertical machines, 5 5-axis machines, a horizontal machine, and we have a water jet. This is kind of what our parts look like. And for instance, the tall part there, that was when the Chernobyl, that's what a fuel nozzle looks like in the closed Chernobyl fuel reactor right now. But we built some of those for some other Russian reactors that Westinghouse went into. But that's what a fuel nozzle in Chernobyl would have looked like. Past practice, we use a database to store all our data. And in that database, we would plot the data within specifications, and then we'd perform all our calculations. But we never used that data. We had millions of data points, and we didn't know what to do with that. So I had this idea that let's let our supervisors look at this data. And so we allowed them to look at the data. Unfortunately, they would do a lot of tweaking with that data. They would adjust things on the machine. So we tended to say that's not the method that we want to go to. So the next step was, and when we collect the data, the machine can tell us if the part's good or the part's bad, but it can't tell us if we're trending towards bad or right in the middle. So we were trying to figure out how to get that data. So we developed this SPC process, again, allowed our supervisors to look at it, and they could not do a very good job at looking at the trending, because if a part started to trend to outside the limit, what they would then do would be to adjust a little bit, and of course it would trend down to the bottom side, then trend back up again, and it wouldn't be stable data. So, so we could only find a defect after the problem happened. So we said, how do we solve this problem? So we took all of our data and we went to the engineering department at Penn State, and we had them look at the data. Unfortunately, what we told the Penn State people was we helped them figure out the problem of what we wanted to find. That wasn't a good method because we kind of steered them the way we thought we wanted to see the data, and it didn't work out. They came up with ideas that we kind of led them to, didn't suit our purpose. So, Lauren will show you that. So then, our next step was we went to Pitt And we took all our data to Pitt, and we said, hey, we have all this, the industrial engineering school at Pitt. That's where we met Lauren, who now is employed by us. We went to Pitt, and we said, here's all this data, you tell us what to do with it. So we found smarter, younger people that could tell us what to do with this abundance of data. And the next part you're going to see is Lauren explaining what their project was, what they came up with, and then what we implemented. But that's how we ended up with millions of data points and not knowing what to do with all this data.
So like Rob said, I was a student at the University of Pittsburgh. I'm actually going to back up a minute and talk more about my experience with everything. So this was my senior project, but the previous summer I interned with L&S, and I became familiar with how they collected and stored data in their data manager database. And the database collects and houses all the features measured off a part on the machine by operation, but a single operation can yield over 100 measurements. So aside from just storing the data, the database will take a filtered sample and plot it within specification limits, and it performs calculations such as sample mean, standard deviation, process capability index, upper and lower control limits, and more. But although it calculates all of these, none were really being used effectively. And we did not like that you had to go in and ask the database for what you wanted to see. And it was calculating control limits, but just based on whatever sample you chose, and it didn't do anything else with them. And the SBC charts were pretty hard to read, and there was just a lot that we thought could be improved. So the problem that L&S gave my team and me was that management found that after a defect occurred, they were able to look back and find indications of failure, but they did not use the data as parts were being made. So here's an example of that problem. You can see there are over 100 parts, and this is just one feature on one operation, plotted on the x-axis versus where the measurement was on the y-axis. And you can see the upper and lower spec limits are the blue lines there. So ignoring the control limits, which were determined later, you can see that the process was running very close to the center line and then suddenly jumped up and continued to run up there. And since the parts were really only being checked for good or not good, it was not caught that something was wrong or had changed. And had there been a system in place, potentially 2 of these defects at least could have been prevented. So the defined goal was to implement a way to catch any statistically unlikely results without having to have a human sit and monitor the data all day, every day, and to adjust the process appropriately before a defect occurred. So through the combined effort of L&S and the University of Pittsburgh, we developed a way to have the data monitor itself. My team and I tested a few things along the way, like checking for time dependency, and we came to the conclusion that control charts would be the best method for L&S at this time. And based on historical data, we created some control charts accompanied by an implementation plan. And then at this point, the semester was over, and I continued the project as an L&S employee. And we created a baseline for each feature by finding upper and lower control limits of plus or minus 3 standard deviations of the sample mean based on samples which could be considered statistically in control. Then we added a subprogram to have the machine probe for in control after it probes for being within specification limits, because specification limits are a little more important. But the machine will alert unlikely results to the operator. Then we know to keep an eye on that feature. And if there appears to be a trend and it's not just a random variation, we can fix the problem before it becomes one. So here's that first example again, and we can consider this an acute change in process likely occurring from a tool change or shift change. This is an example where the operation is completely in control and there are no obvious indications of it trending out of control. This one is a little more interesting. This is a drift example, likely the result of gradual tool wear. And this sample shows that it will soon go out of specification limits if nothing changes. And the addition of limit standards for the future will prevent such an instance probably about 20 or so parts sooner. Here we can use this data to identify an instance of something that went wrong, probably a tool break or something, by seeing 3 examples having a similar variation at the same time. So we can use this as a counter for preventative maintenance in the future. That is all for where we are now, but this is nowhere near the end. We are currently working on a second project with the University of Pittsburgh, but this time with a graduate student in the Industrial Engineering Department to take this even further. And they're applying predictive multivariate statistical methods to be able to identify a problem when it's going to occur and what it will be, rather than wait for the process to go out of control and then look into it. Questions? Yes?
If I understand correctly. If I understand correctly, from my own operations management classes, I mean, those are X bar, R bar type charts. What you're trying to do is eliminate rework and parts that have to be thrown away, which are very expensive. Mm-hmm. How did the work that you were talking about, how did that affect the bottom line in terms of those goals?
Having the limits in place that'll say, hey, something weird is going on because you don't normally run outside of these limits, will allow us to, like the one where it was drifting, it was going to slowly go out of control, and we wouldn't, and well, not slowly out of control, out of specification limits, and we wouldn't have caught that until it was too late. So now the machine will alert and say, hey, something's weird here, and then you can see that downward trend and say, okay, it's time to change the tool.
It's an immediate alert now,
Yeah.
instead of finding out at the inspection station that you have a
Right.
problem. Okay, got it.
Right now, typically, we have no parts that make it to inspection that have a dimensional problem. They may have a nick, ding, something like that, but we have caught all the dimensional issues with either the probe, and we're around, you asked for a number, we're around 3% scrap level now. We'd like to get it even lower than that. For Six Sigma tolerance, and we're machining plus or minus 1,000, so it's picking up most of that. We also use the probe. Pretty much any scrap that we get is somebody did something stupid. It's not that the machine did it. They rammed into the part. They didn't set a number right. But we even have it set up that our probe comes down and looks at if there's a hole that has to be in a certain location. It probes that and says, I'm on the machine right, you can start. If it comes down and that hole's not there, it'll say, hey, you put me on the machine wrong. You need to relook at the part. Yeah, because that's what we're finding most of our problem is just the operator not paying attention. The typical tool wear, those type of things, we're not running into that. Other than if a tool breaks in the middle, that's something you can't predict.
You may want to hit him up for a raise.
No.
Recognizing that the data was sitting on the machines, or excuse me, or on charts or somewhere, but it was not being utilized, and your project was really trying to make it actionable. Mm-hmm. Now that you've seen, you've got, which I guess you probably didn't have before, some notifications that occur and enunciate so the machine operator can either take a different action or not do something. What have you seen as the investment change, where you've looked at data that was lying around and now you say, I have to spend more money either adding something to the machine, getting another probe, connecting wires to make this synchronized so you really can make it operational to where you want to go in the future?
Right now, I think we took the most economical solution we already have the programs that know how to probe, so then we just set in another. It goes down and probes again, and then all it took was just changing the alert to say you're out of tolerance and stopping versus, hey, something's going on, but keep running.
Where most of the money was spent in this deal was nobody else that we could find was doing this. So we went down a lot of wrong paths. And every time we try something, we want to do something different, it's not the right path because nobody's doing this. We had people from Moog visit us, and what they use is they have a room filled with mathematicians where they do this manually. So we've asked around, how do other people do this? And there's not very many people that we have found that do it this way. So once we've done it, the investment isn't bad for where we have to go to next, but we did spend a lot of money down a lot of wrong paths trying to collect all this data and figure out how to do it.
Maybe stop making parts and go to the consultant showing people.
Well, interesting enough, all of these things are off the shelf. Everything here you can just go to a catalog and buy. There's nothing written especially for us. And we thought we were going to go down that path too, of maybe using this as a consulting service. But it's, by the time you get the server and all those things, there's a lot of technical expertise, software, IS support that we just can't provide. So, and our next plan is to implement this at our San Jose facility. Now they do commercial work, but we're hoping that will work out there, that they won't get very much scrap either.
Yeah, I was just curious on your transition from the way you were collecting all your data previously to transitioning to a big data solution. Did you have to update all your instruments and your machines to push data into a new solution, or did you how did you migrate all your data, and was that a lengthy process?
The lengthy process was finding someone that does this. The machine always had a probe, so it always could get the data. Obviously, you had to move it to a server. Then there was a company called, Refresh Your Memory, out in Montana. He had more of an Excel program that took this data in and could pump that data. So it was finding all these. That's why I said it was off the shelf. But once we found the Refresh Your Data guy out in Montana, then we had a good place to collect all this data. And from there, it kind of blossomed from there once we found that guy. Okay.
Great, thanks.